Today, let us discuss about the chemistry of nucleic acids. Now, if we are taking nucleic acid, what is studied as a genetic material proposed by different scientists, by different experiments. Now we have to go for the chemistry of nucleic acids. Now if we are taking a nucleic acid, either RNA or DNA, and each one is being formed of a long chain or a polymer of subunits called nucleotides. Subunits called nucleotides. So a nucleotide is nothing but a subunit of nucleic acids. Now if we will discuss about the nucleotide later in detail. Now if you are taking a nucleotide, it is formed of three components. One, a pentose sugar. Two, a nitrogenous base. And three, that is a phosphoric acid molecule. Here I represent a symbol diagram, a pentose sugar, 5-carbon sugar, then a phosphoric acid molecule and a base. Where are they attached? We will see later. So three components together form one unit, subunit called nucleotide, which is a subunit of either RNA or DNA. Now, let's talk about first one, the pentose sugar. You already studied something about this one in your 11th standard. So anyway, you want to recall those things. So based on the nature of the sugar present, the nucleic acids are classified into two types. You know that one, RNA and DNA. These are the two types of nucleic acids. RNA contains a ribose sugar and DNA contains a deoxyribose sugar. And both are pentose sugars having 5 carbon atoms. Now the only difference between these two. Now in the carbon 2, if you are taking carbon 2, to which attach a hydroxyl group in the case of ribose sugar. So ribose sugar has hydroxyl group attached to the second carbon. But in the case of deoxyribose sugar, it is having only the hydrogen group attached to the second carbon. That means the deoxyribose sugar is one oxygen atom less than that of a ribose sugar. One oxygen atom less than that of what is called ribose sugar. So there you have the second position hydroxyl group, and here we have only the hydrogen group, one atom of oxygen less in the case of deoxyribose sugar than what we have the ribose sugar. So the name of the nucleic acid is based on the sugar it contained, either RNA or DNA. Now the second component. The second component, if you are taking, that is nothing but a base, a nitrogen containing double ring compound or a single ring compound. We can say heterocyclic compounds or heterocyclic nitrogenous bases. So in the case of base, so it is considered as a base because it accepts hydrogen, ion or proton from the medium in which it is there. So that is the nature of the base. You know that one, a base is the one which accepts hydrogen, ion or proton from the medium. So accordingly we have the bases. Since they contain nitrogen in them, they are called nitrogenous bases. And these are all heterocyclic ring compounds. See, this is one ring, another ring. Now we have two different types of nitrogenous bases. They are grouped under two different types of nitrogenous bases. Let's take here. So we have nitrogen bases. Two groups we already studied in 11th standard. One purines, another one pyrimidines. Two different groups. They are classified into two different groups, nitrogen containing compound. The purines are double ring compound. Now I just drew the skeleton of purine. This is a purine having two rings, heterocyclic ring compound with a nitrogen here and there. So actually we have just nitrogen compounds. 5 nitrogen atoms are present in the case of purine and 3 nitrogen atoms are present in the case of pyrimidine. We'll talk about later now. So the purine skeleton having one benzene ring, another one what is called imidazole ring. Now whereas a pyrimidine, it is having only the benzene ring. Now if you are taking purine, there are two types of purines. One adenine, another one guanine. While we are representing in the chain, we are using the letters A and then G. Suppose you are writing A and G referring to the adenine and guanine. So these are the two types of purines. And pyrimidines, we have three types. One, cytosine. Two, thymine. And the third one, uracil. So these are the just actually three types of pyrimidines. Now, if you are taking thymine and then what is called uracil, they are differing only in one place. If you are taking, for example, I am taking the fifth position. In the case of uracil, what we have actually hydrogen. This is uracil. If we have thymine, we have what's called actually methyl group. So this is methyl group, and now we have thymine is having methyl group in position 5, whereas uracil is having only hydrogen in that place. That's why the another name for thymine is also 5-methyl uracil. The another name for this one, 5-methyl uracil. This is the only difference between what is called thymine and uracil. If you are taking either RNA or DNA, each one is being formed of 4 types of nucleotides. Each one is formed of 4 types of nucleotides. I mentioned here adenine, guanine, cytosine, thymine and uracil. Now of these, so cytosine is represented by C, thymine is represented by T, uracil is represented by U. If you are taking DNA, it is being formed of 4 nucleotides. One adenine nucleotide, guanine nucleotide, cytosine nucleotide and thymine nucleotide. If you are taking what's called RNA, it is being formed of again 4 types of nucleotides, adenine, guanine, cytosine but uracil. So instead of thymine you have uracil. So the first 3 bases are common to both, that is DNA and RNA. You see that one? The first 3 bases are common to both DNA and RNA, whereas the 4th base is different. Here in DNA we have thymine, in just RNA, instead of thymine we have uracil. So as we have studied already, I want to recall only. So we have 5 different types of bases grouped under 2 headings, purines and pyrimidines. Purines are of 2 types, pyrimidines are of again 3 types. So purines are of 2 types and pyrimidines are of 3 types. Out of the 5 nitrogenous bases, 4 nitrogenous bases are present either in RNA or DNA. So this is about the nitrogenous bases. Now we have to go for the next one, the phosphoric acid. Now let us talk about the 3rd component of a nucleotide, that is the functional phosphate group. Now it is derived from the phosphoric acid. So it is having, you see that one, 3 active hydroxyl groups. 3 active hydroxyl groups. Out of these 3 hydroxyl groups, 2 hydroxyl groups are taking part in the formation of nucleic acid. One is left. Now this phosphoric acid, because of the presence of phosphoric acid, it gives the property of an acid 2, that is the nucleic acid. So an acid is the one, you know that one, which releases hydrogen ions or proton to the medium. So the acidic nature of the nucleic acid is because of this phosphoric acid molecule. Now actually the phosphoric acid molecules are joined together, the phosphate molecules in the nucleic acid, by means of a bond, what is called ester bond. The bond between the phosphates of adjacent nucleotides is called the ester bond. And what's happening? Now it forms actually an ester bond with the 3 carbon of that is the pentose sugar at one end. Suppose I am taking here simply, this is 1, It also forms what is called an ester bond with the 5 carbon of adjacent sugar nucleotide. Adjacent sugar nucleotide. So it forms a phosphodiester bond. One with what is called the third carbon, that is a hydroxyl group of the third carbon of the preceding sugar, and the fifth carbon of the succeeding sugar. So we are having what is called phosphodiester bond. This is one ester bond, this is another ester bond. It is between the phosphate group and the hydroxyl group of the third carbon of the preceding sugar, and with the hydroxyl group of the fifth carbon of the succeeding sugar. So we have received what is called 2 ester bonds. This is 1 and this is 2. That's fine. The adjacent nucleotides are connected with one another by what is called phosphodiester bond. Now when a phosphodiester bond is formed, in the case of this one, for example, 2 hydroxyl groups are taking part, leaving 1. This is one hydroxyl group taking part in a bond, and this is another hydroxyl group taking part in a bond. So what is happening? We have this is with what is called either with the third carbon or with the fifth carbon, and this is with this actually attached to the third carbon or the fifth carbon, and likewise here also it is attached to the third or fifth carbon. So at the formation of phosphodiester bond, we have actually left one oxygen atom. That oxygen atom is negatively charged. One oxygen atom is negatively charged. So that is why you see that one nucleic acid is aptly a negatively charged molecule. This is happening because of the diester formation. After diester formation between the successive sugars, between the 2 nucleotides, one oxygen atom is left as a negatively charged one, and that is why the nucleic acid is negatively charged. Now, the presence of phosphate group ensures the retention of nucleic acid either within the cell or we can say within a nuclear membrane. So because of this what is called oxygen atom or because of what is called the phosphate molecule, now the nucleic acid is being retained inside the cell membrane or we can say inside the nuclear membrane. That is the nature of the functional group. So the negativity is because of what is called the functional group phosphate that happen after the formation of a phosphodiester bond. One oxygen is left as a negatively charged, that gives negative charge for the whole nucleic acid. Because of what is the function of the phosphate group? The phosphate group normally ensures the retention of nucleic acids within a nucleus or nuclear membrane or within a cell membrane, we can say either way. So this is the property of functional group of phosphate. So we have seen already the 3 just actually the components of a nucleotide. 1, a pentose sugar, 2, a nitrogen base, and the third one what we have a phosphate group or a phosphoric acid molecule. Now the nucleic acids are the polymers of nucleotides. If we are taking a nucleotide, it is being formed of 3 components as I mentioned earlier. 1, a pentose sugar, this is number 1. Number 2, a nitrogen base, any one of the 4 nitrogenous bases. Suppose we are taking DNA, adenine, guanine, cytosine and thymine. And then a molecular phosphoric acid, this is the third one, derived from actually that is the phosphate that is derived from the phosphoric acid. Now, a pentose sugar with a nitrogen base is called nucleoside. A pentose sugar with a nitrogen base is called a nucleoside. Now here this is carbon 1. Now the nitrogen base is connected to the pentose sugar to the first carbon atom. Now I am drawing one again here represented. This is what we have the base as represented here. Okay, so the nitrogen base is linked to the pentose sugar to the first carbon of the pentose sugar by means of a linkage. As it is connected to the first carbon and also the NH group of the nitrogen base, it is called L1 glycosidic linkage. L1 glycosidic linkage. So the linkage between what we have the hydroxyl group and also we have the hydrogen group. So now the base is connected to the first carbon of the pentose sugar, that is deoxyribose sugar in DNA, by means of a linkage. The name of the linkage is called L1 glycosidic linkage. I do the diagram here also. This is number 1. That forms what is called a nucleoside. So a pentose sugar with the nitrogen base by means of what is called glycosidic linkage is called a nucleoside. Then when phosphate is added to the nucleoside, then it becomes a nucleotide. The phosphate group is added either to, that is what we have here, this is a phosphate group attached, or to the third carbon, So the phosphate group when attached to the nucleoside then becomes what is called a nucleotide. It is attached either to the fifth carbon or to the third carbon of the same nucleotide where the base is attached. So that becomes what is called nucleotide. A nucleoside is formed of what is called a pentose sugar and nitrogen base. The linkage between pentose sugar and nitrogen base is called L1 glycosidic linkage. The linkage occurs between the first carbon atom and the NH group formed in the nitrogen base. So if it is, for example, adenine, then the nucleoside is called adenosine, guanosine, cytosine, thymidine. If it is actually, that is DNA, deoxyadenosine, deoxyguanosine, deoxycytidine, deoxyuridine. These are all what we have the nucleosides. When phosphate group is added, it becomes a nucleotide. A nucleotide is nothing but an acid. For example, deoxyadenylic acid, deoxyguanylic acid, that is what is called thymidinic acid, deoxycytidinic acid. So a nucleotide is nothing but an acid because of the presence of phosphate. So the phosphate group is attached either to the fifth carbon or to the third carbon of the same sugar to which the base is attached to the first carbon. So this is what we call the skeleton of a nucleotide. So pentose sugar to base, L1 glycosidic linkage. The linkage between the phosphate group is called phosphoester linkage. Now this is the phosphate group, this is the one, and here also represented this linkage what we have phosphoester linkage. Now one nucleotide is connected to the adjacent nucleotide. Suppose this is one nucleotide, I am taking that one. Okay, this is a phosphate group. This is another nucleotide. So there are two linkages. This is another sugar. So there are two linkages, that is between the phosphate group and the third carbon atom, and also between the phosphate group and the fifth carbon atom. Here this is fifth, and there we have three, like that. So in such a manner you see that one, the phosphate group is attached to either to the third carbon of the preceding sugar or to the fifth carbon of the succeeding sugar. So two ester linkages being formed. That's why the adjacent two nucleotides are connected with one another by means of phosphodiester bonds. So the components and the bonds that link the components of the sugars of the adjacent nucleotides are called phosphodiester bonds or phosphodiester linkages. So the bonds that link actually the sugar components of the adjacent nucleotides are called phosphodiester bonds or linkages. the two strands of DNA are anti-parallel in nature. One strand is running in 5'3' direction, another strand is running in 3'5' direction. That means each strand has two distinct ends, either in RNA or in the case of DNA, and they are designated by symbols 5' and 3'. 5', 3'. That is a distinct end. Now what is 5' refers to? The 5' refers to the number of carbon atom, that is a carbon in the pentose sugar, to which the phosphate group is attached. You see that one. 5' is the number in the pentose sugar to which the phosphate, the free phosphate moiety or group is attached. That refers to 5'. So at one end we have free phosphate group here. You see I mentioned. In another end, 3' end, we have free hydroxyl group of the third carbon in the pentose sugar. So this is a free hydroxyl group I mentioned here, third end. So 3' end refers to the hydroxyl group, free hydroxyl group attached to the third carbon of the pentose sugar. That denotes 5', 3', that one. 5' refers to free phosphate group, 3' refers to, that is what's called free hydroxyl group. So in one strand at one end we have free phosphate group attached to the fifth carbon, and another end we have free hydroxyl group attached to the third carbon of the pentose sugar. Now in the case of RNA, we have hydroxyl group attached to the second carbon in the ribose sugar. So this is what I mentioned, deoxyribose sugar. If you are just adding this hydroxyl group here, it refers to the ribose sugar. So this is an additional group that is found attached to the second carbon of the pentose sugar in, that is RNA. Now, that is a direction. What we can say, this is a direction. So understanding the direction of 5', 3' is normally critical for understanding the processes like replication and transcription, because the transcription or replication, that means either transcription or replication always occurs in 5', 3' directions. That's why understanding the 5', 3' direction in nucleic acids is critical for understanding the process of transcription or replication of DNA. So in both the cases, either in transcription or in the case of replication process, it is proceeding always in 5', 3' direction. That's why you have to know what is 5', 3' direction. Based on the X-ray diffraction study of Maurice Wilkins and Rosalind Franklin in 1952, James D. Watson and Francis Crick proposed the molecular model of DNA, the double helical model of DNA. We have already seen the DNA is a double helix with the two strands which are anti-parallel, running in opposite directions, etc. Now see here. So now here represented what is called the double helical model of DNA. This is the two strand we have running in 5', 3' directions. The same is, that is expanded in the form of letters. S stands for sugar, then P stands for the phosphate group, A stands for adenine, that is T stands for, that is thymine, G stands for guanine, and C stands for cytosine. Now, the backbone of each strand is formed of sugar and phosphate. These two are running in what we have in a zigzag manner alternately. Sugar, phosphate, sugar, phosphate, sugar, phosphate, etc. Now the phosphate is attached to, you see here, the third carbon of this sugar and the fifth carbon of this sugar through phosphodiester bond. Phosphodiester bond. So the backbone sugar and phosphoric acid or the phosphate are actually running alternately, linked together by means of phosphodiester bond, what I seen already. I'll show it once again. Now with the nitrogenous bases facing the center. Now according to Watson and Crick model, it is just like a twisted ladder having, that is, a distance of 20 angstrom. Distance of 20 angstrom. That is the diameter of, that is the DNA. This is the diameter. Is about 20 angstrom. Or we can say 2 nanometer. 20 angstrom or 2 nanometer. Now, one of the important aspects of DNA model proposed by Watson and Crick is nothing but the base pairing. Is one of the important aspects of what is called the model, based on the observations of a person by name Erwin Chargaff. Erwin Chargaff. This is called actually base pair rule proposed by Erwin Chargaff, or Chargaff's base pair rule. So according to the Erwin Chargaff's base pair rule, the two strands being, that is, complementary. One strand is having base sequence. If you know the base sequence of one strand, you can find out the base sequence of another strand. That is what's called complementary to each other. Now what is a base pairing? The number of purine is equal to number of pyrimidine. The number of purine is equal to number of pyrimidine. This is a base pair rule. They exist in 1:1 ratio. They exist in 1:1 ratio. That means the purine includes adenine and guanine. That means the number of adenine is equal to number of guanine, as they belong to what's called the purine. Number of adenine is equal to number of, that is, guanine. And number of, actually that's purine, that is number, I made a mistake here. The number of adenine is equal to the number of thymine, because purine is equal to pyrimidine, A is coming under purine and T is coming under pyrimidine. And similarly, number of guanine is equal to, that is, number of cytosine. They also exist in 1:1 ratio and equal to 1. A is equal to T, G is equal to C. And similarly, if you are taking the purines, we have just A plus G is equal to T plus C. This is constant because A is equal to T and G is equal to C. And similarly, A plus C is equal to T plus G. This is also correct one because A is equal to T and G is equal to C. Then A plus T, if you are taking, for example, I am writing here once again, A plus T need not be equal to G plus C. So A plus G is equal to T plus C, A plus C is equal to T plus G, A plus T need not be equal to G plus C. That's a concept, the base pair rule. So the number of adenine is always equal to the number of just actually thymine. The number of guanine is always equal to the number of cytosine. And similarly, the purine and the pyrimidine exist in 1:1 ratio. So this is what we have. If you know the value of A, one can find the value of what is called T. If you know the value of G, one can find the value of C. There are, we have problems. Let's talk about in the NEET class how to find out. That's the answer for each one. Okay, now this is one. So this is called Erwin Chargaff base pair rule. This is one of the principle, the basic concept used in the case of Watson and Crick model. Now I am taking here, I mentioned already. Now the phosphate group is attached to the fifth carbon. Now this is the fifth carbon. I am taking one strand. Strand A. This is strand A. I am taking only two nucleotides. This is strand B. Strand A, strand B. Now one end is 5', another end is, you know that one, 3'. At the 5' end we have the free phosphate group, and the 3' end we have the free hydroxyl group. Now I am drawing the sugars in what is called inverted position to show the location. So here you see that one end is starting with the 5', here it is starting with 3', ending with the 3', ending with the 5'. So the phosphate group is attached to the fifth carbon as well as to the third carbon. So when a nucleotide is formed, Now this is one nucleotide, what I am mentioning. This is one nucleotide. A nucleotide is formed of a sugar, a base and a phosphoric acid molecule. Likewise, if we are taking this, actually this is a nucleotide. This is a nucleotide. That is a phosphoric acid molecule, a sugar, and then just again you see that one, a nitrogen base. I am just making mistake, it's just sorry for it. So this is a nucleotide. So a nucleotide is formed of, you see that one, here the free phosphate group and then the pentose sugar and a base adenine. So it is adenylate acid. This is a nucleotide. This is another nucleotide. You see that one, this is another nucleotide formed of a phosphoric acid, a pentose sugar and nitrogen base. So I represent only two nucleotides instead of just lengthening the chains. Now you see that one, the phosphate group is attached to the fifth carbon, that's why the end is 5 dash. And they end with the 3 dash, where we have the free hydroxyl group, what I mentioned here. And same one here, you see that one 3 dash end with the free hydroxyl group and 5 dash end with the free phosphate group. Now we have, according to the base pair rule, I mentioned A is always forming a pair with the T, G is always forming a pair with the C. Now this is the one. A is always forming a pair with the T, sharing 2 hydrogen bonds. This is the hydrogen bonds. And T is pairing with the C with the 3 hydrogen bonds. So the hydrogen bonds actually 3 here, 2. So the 2 strands are being held together by means of hydrogen bonds. The number of hydrogen bonds vary between A and T and then G and C. Between A and T, 2 hydrogen bonds, and between G and C, we have 3 hydrogen bonds. This hypothesis is called Pauling's hypothesis. Sharing of hydrogens between the 2 strands is called Pauling's hypothesis. He proposed his hypothesis, the sharing of hydrogen atoms between A and T, between just G and C. So because of the sharing of hydrogen atoms, and because of between one purine and one pyrimidine, between the 2 chains, the total diameter between the 2 strands is constant, that is about 20 angstrom. So in one place we have, this is what is called a purine and this is pyrimidine. So we have alternately the arrangement of what we have the bases or the nucleotides giving a constant diameter between the 2 strands, what's called 20 angstrom. So what we describe is nothing but the D model of DNA. So normally the DNA exhibits polymorphism. We have A, B, C, D, E DNA and also Z DNA. The A, that is other DNA, A, C, D, E, they are not biologically active forms. Only the B DNA is active. The B DNA is the only DNA which is biologically active. So the model proposed here is nothing but what's called B DNA, the most biologically active molecule of DNA. Other DNAs are less active. Now another DNA, what I mentioned about what we call the Z DNA. The Z DNA, you see that one, it is a left-handed DNA. Left-handed DNA proposed by 2 different people or groups we can say. One group from New Zealand, another group from India. Both just propose the Z DNA or left-handed DNA. Here the helix in the case of B DNA is right-handed helix. In the case of, we can say dextral. In the case of what we have Z DNA, the helix is in the left-handed nature and that is called sinistral. Dextral, right-handed, sinistral, left-handed, that's a coil. So this is main difference between what we have is the DNA and also B DNA. We have many differences. Even if we are taking what's called the distance diameter, here it is 20 angstrom B DNA, but in the case of Z DNA, it is 18 angstrom. And also if you are taking, for example, the distance of one pitch, the distance between what we have the bases of the nucleotides, all different, and that is for only the entrance point of view. I don't want to discuss that one, it's not there in the board syllabus. Anyway, we would like to know all these facts related to. So this is what we have expansion of the molecular structure here, representing the attachment of the phosphate group and the attachment of the sugar to the nitrogenous bases. At one end we are always having 5' free end of phosphate, another end we have 3' in one chain, the hydroxyl group of the third carbon free, and likewise here also the hydroxyl group free at one end and the phosphate group free at another end. So there are also so many problems related to what we have the base pairing. We don't want now. Now the two chains exhibit what's called complementarity. The two chains are complementary to each other. If we know the sequence of one chain, for example, A, G, C, T, A, C, T. This is actually one chain with a sequence of nucleotides A, G, C, T, A, C, T. So if the two chains are complementary, one can predict the bases found in the opposite chain. Because A is always forming a pair with the T, G is always forming a pair with the C, C is always forming a pair with the G, once again A, T, G, then A. So this is called complementary or complementarity. The two strands are being complementary to each other. That is one of the properties of the DNA proposed by Watson and Crick model. So one can know, one can predict, that is what we have the bases found in the opposite chain, the corresponding chain, if we know the base sequence in one chain are given.